Hello again, and tonight's presentation is even bigger, brighter satellites. This is as a result of my seeing that, because let's just say I'm a SpaceX fan, and I saw them launch a satellite, and I hadn't heard of it before. It's called BlueWalker 3, and I said, let me learn about that. And when I learned about it, I said, this thing has got to be very bright, reflective, and aside from the International Space Station, it's got to be the next brightest thing in the sky. And it's cruising across the sky at a little bit higher altitude than the space station. So how come I haven't heard about this thing? And I found out why, which is, no, all of our attention is on them bright damn Starlink things from SpaceX, because it's Elon and we don't like Elon. And okay, fine. So anyway, tonight we're going to be talking about, there's other bigger, brighter things already out there, and there are newer, bigger, brighter things that are being put up there. And you don't see a lot of that in the coverage, but you hear about it tonight. So this is information. It's not based upon fear, uncertainty, and doubt, which is FUD. It's a great thing used by people who want to make you be afraid, be very afraid. Lots of people talk about SpaceX Starlink satellites being highly reflective and using all sorts of radio frequencies. And every Starlink launch and every satellite is approved by the US Federal Aviation Administration. And all of the radio frequencies used by Starlink are registered with the US Federal Communications Commission. There's no rogue nature going on here. So if you look at the pictures on the right there, the one at the top is when the satellites have just been launched and they've separated out and they want to use their krypton gas-based ion thrusters to get up to their much higher altitude. And when they do that, if they had their solar panel flying as it would normally when they're in higher altitude orbit, you see how the solar panel kind of like is Z-fold and it goes up off the plate of the satellite, which is the body of the satellite. And when they're flying in lower altitude orbit on their way up to their normal altitude, there's still atmospheric drag. There's little bits of molecules of gas that are left in the atmosphere. They're not quite in a vacuum. So if they flew with the shark fin, as they call it, vertical, there would be drag and it might not have enough ion propulsion fuel to make it up to orbit. So they lay the solar panel out flat as it climbs up to orbit. And when it does that, and it happens to be late in the afternoon or early in the morning, the sun angle will catch off the solar panel, not the body of the satellite, but of the solar panel, which is highly reflective. And if you look at it, the solar panel, solar radiation side has to face upward. That way it can power the satellite, but the bottom doesn't. So what they did was they painted the bottom side of the solar panels dark gray, which reduced their albedo, which reduces their reflectivity. So they've gotten a lot darker than they once were. But as they go up to their orbital position, that's the only time you can see them. Once they're up at their orbital positions, like, where did they go? You can't see them easily naked eye anymore because the big bright part, the shark fin, which is their solar panel, is vertical and it's kind of waffle shaped. But the actual body of the bottom of the satellite is a couple of squares of dark material, which is the actual flat radio antennas, and the dark silver is the body of the satellite. And it's kind of a very fine, dimply, ceramic-y kind of coating, which it makes it not very reflective. It scatters light when the light hits it. So we're not going to spend a lot of time after this talking about the Starlink satellites, other than to compare them against the BlueWalker 3 satellite from AST SpaceMobile. Now, you might hear more about those in the future because AST wants to resell their satellite services to all the major mobile phone service providers, because when you hear about things like, hey, my Apple phone has satellite service, that's not with Starlink. That's with a group like SpaceMobile. And you'll be able to use normal mobile phone radio frequencies to communicate with low orbiting satellites in case you have an area where there's no good coverage. So if AT&T and Verizon and T-Mobile don't want to spend the money to cover all the way out in the middle of nowhere, the satellites that will be zooming overhead will give you your mobile phone service coverage. Now, AST SpaceMobile is not a rogue operation. Their launch was FAA approved, and their frequencies that they're using are registered with the U.S. Federal Communications Commission. And the oddball is that the BlueWalker 3 satellite was actually launched by a SpaceX Falcon 9 rocket. So SpaceX is making money any way they can, and given the loss of Russian launch vehicles by Western influences, they're launching competitors. So this is just another competitor they're doing launch services for. But when you think about satellites and people go, looks pretty crowded up there, that's part of the FUD, the fear, uncertainty, and doubt. So if you look at this lower left picture and you say, if the Earth is how many thousand miles in diameter, and I'm looking at a satellite that's as big as the state of Florida, it's not that big. So if you shrink down the satellites to the point where they are scaled at the same scaling level as you're showing the planet Earth, all the satellites would disappear. There wouldn't be even a single pixel available to see them. That's simply a matter of scaling. So what they do, because if you want to make it look like it's bad stuff, you make it look like this swarming ball of bees around the planet. But the only way you can actually wind up with that as your end image or your end video is to shrink the Earth down and inflate the size of the satellites by about 1,000 plus each. But the actual spacing between orbits is considerable. Satellites are horizontally separated by miles or kilometers, and their orbits are angularly spaced, inclination-wise, by fractions of a degree. And then the actual altitude, so each of those has a stack of slots. So as you get larger and larger diameter orbits, because the altitude is increasing, you get more and more space for satellites. Or to quote Elon Musk, space is big. And it is. Now, there's only so many slots to go around, and I think when we get to around 30,000 satellites up there, it'll be time for concern. But it's the uncontrolled stuff and the debris fields, usually caused by satellites that accidentally go boom, which that's rare, or governments that blow up their satellites to show how they can take out other countries' satellites, like China has done, Russia has done, and the US has done. So when you hear about Russia blew up a satellite and created all this debris, yeah, we did the same thing, but we took out a very low Earth orbiting satellite, and when we did, it kind of fell back quickly. So not that that's a good thing to do, but different countries do it differently. This is my other favorite one to show when people talk about how bright satellites are. Bright is a comparative thing. And if you go in and you fool with the evidence, you can make it look horrific, not just unacceptable or bad, but horrific. So here's a picture of a fast-moving satellite, the one up at the upper right here. It's a fast-moving satellite, and it looks really bad. Look how much brighter it is than all those background stars. Oh, well, I'm going to be honest and tell you what I did. In the lower left is a star that was in the same field of view. Notice how that star is big, bright, and fuzzy, like it's not a sharp image of the star. Why is that? Oh, because that's how badly overexposed the image was in order to make the satellite look evil. If I take a star and I overexpose the image until I've got the star glowing with a fog around it, I wouldn't normally do that. But if I want to make the satellite look bad, I've got to make the satellite look really bright. So I'll just overexpose the image. The second thing is, if there are other similarly bright stars in the field, I've got to remove those. So although the star in the lower left is overexposed, the star in the lower right is also overexposed. But if I didn't overexpose it, it might actually be the second brightest thing in the image. But by it being overexposed, and I remove both these star patterns from the resultant image, I can make the satellite look like the brightest thing in the night sky. But then, just to make things look worse, which is not evident here, I adjusted the graphics of the image so that brightness was bumped up by 15%, contrast was bumped up by 8%, sharpness was bumped up by 15%. The end result is, if you had a small, dim star, I actually made the star smaller because I sharpened the image and I increased the brightness. So I basically cut away around the outer edge of the star by making it sharper. And then I brightened the resulting image, which made the bright stuff look brighter. So the satellite looked really bright. So the next time you see a picture of, look how horrible that satellite is going across the sky, ask for details about the image, because the person putting forth the image could have been there to just churn some FUD about how evil satellites are and didn't really tell you all the details that I just told you. But you know, I've looked at many an image claiming to be of bad satellites, and then when you start looking at the details, you realize, yes, it was a satellite. Yes, it was reflective. But there's a lot of other things in the image that say it's not as bad as you think it is. And besides that, there's information that will tell you where the satellite's going to be in the sky at any particular point in time. So you can process that out easily. And when you realize this may actually be a stack of images that they pasted together so you have this nice solid streak, as opposed to a video where you'll see the satellite very quickly moving across the sky. What's that saying? Don't believe anything you see and only half of what you heard. Let's compare apples and apples here. The picture in the upper right is of the BlueWalker 3 radio antenna. This is just a radio antenna, not the solar panel. This is just a radio antenna on the ground before they attached it to the satellite for inclusion in the rocket to launch to the mission. The little blue things in the back, those are people. So that will give you an indication of the square area of sky that this thing will be occluding. And when you look at it, there's white between every one of those little round tan-colored things. And every one of those little round tan-colored things is actually a shallow parabolic dish antenna. So it's reflective, it's white. Every one of them has a little concave reflector called a parabolic antenna that's tan in color, not black. So that thing is going to be pretty bright up in space. On the other hand, the little dark inset thing here is a single Starlink antenna, bottom side comparison. So if you were to say, let's take out 1, 2, 3, 4, 5, 6. 6 of these little tan panels is one Starlink satellite. And this is only one of the BlueWalker 3 class satellites. And they plan on putting many of those up in orbit. Now, how big is the actual That's just the antenna. This is not the solar panel. The solar panel is probably about half the size of this, because that much radio stuff is going to need a lot of electricity. So the BlueWalker 3 radio antenna square area is 64.4 square meters, or 693 square feet. Think of it as it's half the size of a basketball court, and it's going to be flying at between lower 500, lower 300, lower 500 kilometers, lower 300 miles. About the same ballpark as SpaceX Starlink satellites. Starlink's a little bit higher. So I went to heavens-above.com and I said, okay, so let's compare apples to apples here. Tell me all of the really bright things that are going overhead in my location tonight. And this is what it came back with. I said, I want to see the really bright stuff. So it's magnitude 3 and brighter. So the numbers don't go from 3 to 0. The numbers actually go from 3 through 0 to negative values. And you'll see that the brightest thing here is the International Space Station at minus 1.5. There's a rocket booster listed here called Atlas Centaur 2, magnitude 3. That's pretty bright. What is an Atlas Centaur 2? Atlas Centaur 2 is a spent second stage rocket booster from 1963. And it's actually moving pretty quickly, but it's in a stable circular orbit. So you can see that at 1748.56, it makes a pass. And then at 1938.17, it makes another pass. It's the same thing. But now, because the sun's a little more lower, the angle is just right. So the brightness goes from magnitude 3 to magnitude 2.4. There's a factor difference of brightness with every 1.0 difference in magnitude. So that's quite a jump in brightness. But what is this 1.5 guy here? That's a Chinese spent rocket booster. What is this Cosmos thing? Yep, that's Russian. The meteor's Russian. How long do these things stay up there? If it's in a stable orbit, pretty much forever. If they get a little lower, then the atmospheric drag will eventually bring them back down. But if they get to a certain altitude, they can stay there for many decades. So people always talk about geostationary satellites. Where are all those geostationary satellites? I did a little research into finding out how they are visible or not visible. And the simple answer is, although they are the biggest and most reflective things up there, these are satellites the size of school buses with basketball court, full court size solar panels with 10-meter radio antennas that actually open up like giant flowers. How come those aren't reflective? They're very far away. They're in geostationary orbit. And the sun angle needs to be just right. So in March and September, during the equinoxes, you can spot them if you know how to look. If you're using a telescope mount that can track the background stars, so the background field stays fixed, the geostationary satellite will actually move slowly across the sky. So here's a table that shows just the US geostationary GOES weather satellites. And not all these are working. The thing labeled as GOES-2 rocket is a second stage booster from 1977. It's been up there for 45 years. None of these things have visual passes because they're too dim. And none of these things actually have all passes. You can't select that because they don't really pass overhead. They're geostationary. They're stationary overhead. So they're kind of futzing with the system. But if you go into a piece of software like Stellarium, you can actually see a band of them going across at the horizon, the celestial horizon. But where are all those Starlink satellites? If you didn't know it or not, there are currently just over 3,000 Starlink satellites up there. The reason why you cannot see them is They're actually dimmer than magnitude 3. Most are in the magnitude 5 or dimmer level. But they're small, even though they're reflective, they're very tiny pinpoints of light. So you're just not going to see them easily. So when they've just been launched, you're going to see them for a month or so. Once they get up to orbit and they take that flat solar array and they bring the shark fin up, there's nothing to reflect back to the ground anymore. And think of it this way, if you're looking for things that are magnitude 4 or dimmer, and you're in a light polluted sky where you can't see stars that are magnitude 4 or dimmer, you're not going to see any of the Starlink satellites up there. So I ran the same analysis looking for magnitude 5 or brighter, and it produced a table with 372 rows in it. Of the 372 rows, 275 of them were Starlink satellites out of the total 3,280 of them up there. The range of brightness was from 3.4 to 5. So they can get too dim to actually be visible. But once you have a long duration exposure, you might see them. Think of all of these deep sky, large scale telescopes. They are going to maybe have a problem with it if they're doing very long duration exposures. But remember what they're trying to spot. They're trying to spot near Earth orbiting objects. So their exposure duration is not going to be that long because then they miss it amongst everything else. So they're taking very sensitive camera flash exposures of the sky very quickly. Now, if you patch all those together in a stack, you'll be able to see an asteroid or a comet or a Starlink satellite or a field of them go by. And that's what their complaint is. I would say if you get a BlueWalker 3 in your field of view and it wants to move across the sky, it's going to be, one step dimmer than the International Space Station, and it will just take out everything that your dim camera is trying to pick up until it goes through. But where is BlueWalker 3? So if you said, how do I go see this? Well, you go to heavens above and you say, show me where BlueWalker Space 3 is. And it will give you, based upon the location that you enter, or it figures out your current location, how bright is BlueWalker 3 going to be? Well, on December 12th, it will go overhead of my house at magnitude 2.5. And it'll be 55 degrees overhead when it gets to its highest point. So 90 is directly overhead. 45 is, halfway up. So it'll be a little more than halfway up, and it'll cross the sky in, about 5 minutes or so. So you can definitely see it trucking across the sky faster than any airplane that's up there. And it does it on a repeated basis. And its orbit is actually oscillating. So the elevation of the orbit is not fixed. So it's not going to stay always at the same place. It's going to oscillate as the Earth rotates under it. So you can actually see that here by the highest elevation going 11, 12, 24, 55, 50, 45, 41, 37. So you can actually see that there's an oscillation going there. But I don't hear a lot about this bright things going overhead. So what's my point? The whole point of the presentation is there's other long existing and recent stuff in orbit that is far brighter than Starlink satellites. Just the other day, Starlink competitor OneWeb, they used a SpaceX Falcon 9 to launch 43 satellites of traditional design. That means a giant square or rectangular bodied satellite, and on the out edges of it, it has two giant tilting solar panels. And they launched 43 of those. And they're slightly higher in orbit than the SpaceX Starlink satellites. So they're going to go across the sky slower. So once those are up there and going overhead at the sunrise and sunset timeframes, they're going to be much brighter and go more slowly across the sky. And as I said, AST SpaceMobile is planning on launching many more of their satellites. In conclusion, you got to look with a wider vision to avoid the fear, uncertainty, and doubt and clickbaiters. Graphical content can be created for an intended purpose. Don't accept it at face value. If it looks horrific, it may be horrific because somebody adjusted the evidence. There are many thousands of items in orbit. Not everything up there is a Starlink satellite. Some of the oldest, brightest stuff has been up there for decades. And I'm not talking about the good stuff like the International Space Station or the Hubble Space Telescope, both of which we've watched go overhead, and everybody was amazed and in awe, and nobody said, that's too bright, because it just is bright because it's got solar panels. There's non-SpaceX space junk up there that's been up there for decades, and not all of it was US launched. Some of the largest and most recent stuff that's up there is larger and brighter than Starlink satellites, and BlueWalker 3 is just one of those, but the geostationary stuff is even bigger and brighter. It's just that it's, 10,000+ miles up there. So it's going to be farther away, and as the light spreads out, it looks dimmer. Everything launched by the US or the EU, European Union, is something that is registered and approved through the US Federal Aviation Agency and the Federal Communications Commission. Everything that is launched, whether it's got approvals or not, gets recognized by the US Space Force. And they monitor everything from space. So it's no longer like radars and cameras on the ground that are monitoring space. They realize, sometimes the weather's not good and we can't monitor it from the ground. So they actually have a satellite in orbit that monitors satellites in orbit. And they monitor not just the satellites they know and can track, they monitor also all the little bits of debris left over by satellite launches. And when governments are stupid enough to blow stuff up, they have to monitor all that stuff down to things the size of a pea. Because a pea, if you're going at 19,000 miles an hour and the pea is coming from the other direction, and it's also going at 19,000 miles an hour, that means the pea is going to give your space station a bad day at 38,000 miles an hour. Not good. So if people want more information about AST SpaceMobile and BlueWalker 3, I've got that. Starlink, obviously, heavens-above.com. And if you want to know more about the U.S. Space Force and their space-based surveillance system, they actually have a specific base here on the ground that does monitor for all that stuff. And they have a fact sheet about it. I just think that the portion of Space Force that does the monitoring has a really cool base division identifier, SPOC, SPOC. Okay, comments or questions?
Yeah, a couple of days ago, an engineer from Artemis was asked, what would happen if a craft coming back from the moon, trying to land on the Earth, has to cut through this sphere of objects and things in the way? And he answered just what you said. He said, they're far between, and there's a lot of space up there, and the chances are that he's not going to hit anything.
And another thing is, they know at what angle, what inclination to position the craft coming back at Mach 20 so that it has zero opportunity to encounter anything. Because if you read about Artemis 1 coming back through, one of the things Artemis 1 has to deal with is the Van Allen belts. And the Van Allen belts are those, nope, can't use those, orbits around the Earth. So there are low Earth orbits, there are medium Earth orbits, there's the Van Allen belts, which is like, you put your satellite there, it's going to be toasted if you leave it there. and then there's the higher altitude, and then there's geosynchronous or geostationary. So when you're coming back from space, you flew out through the Van Allen belts to get out to space. If you're coming back at such a high speed, you're not going to stay in the Van Allen belt long enough for it to be a problem. So if you want to avoid everything we've ever launched, come back in by way of the Van Allen belts, never a problem. We get the same question. Okay, we sent spacecraft out to the outer parts of the solar system. They went right through the asteroid belt? Yes. It is not Star Wars, folks. You don't have to fly dodge them to avoid the asteroids. Asteroids, there's tens of thousands of them, but space be big and spacecraft be small. So it never said, should I avoid all the asteroids in the asteroid belt? They just said, no, you're going fast enough. You're doing 30,000+ miles an hour. Just fly through like they aren't there. The probability of hitting an asteroid is so small that you might ask the same question. You know, when Cassini was zipping around Saturn, did it ever encounter the rings of Saturn? Oh, it punched through the rings of Saturn up and down through those rings like they were nothing. Really? Well, it's just mostly ice. There's very little rocky debris in there. And the actual distance separating all the bigger chunks is wide enough that it was never a problem. So things be small, space be big, and stuff be moving really fast. So
yeah, but the Webb Space Telescope and the International Space Station were both hit by debris, right?
And why was that? Okay, I can tell you why the ISS gets hit by debris. It's been up there a really long time, and it's at a orbit that is not the lowest of low Earth orbits, and it's not the highest of low Earth orbits. It's right in the sweet spot in the middle. So it has the unenviable opportunity to hang out in the dirtiest parts of low Earth orbit. So it has to do a lot of moving around and avoiding. And the James Webb Space Telescope, they did a little correction recently because they were doing a stupid. They were pointing the telescope in the direction of targets that they had queued up for observing, but those targets made the telescope point in the direction of cometary trails. And they figured out that's probably not a healthy thing to do for the mirror. So they stopped doing that. But yeah, if you're up there long enough and you're moving slow enough and the other stuff's moving in the other direction fast enough, you're going to get hit. And you can get hit by really, really small stuff and have a bad day. If you get hit by big stuff, you might have been able to see it coming, but if you can't adjust your course, that's going to be a problem.
It's actually very difficult to actually find those satellites to fix, because you need to, like in the case, to find the space station, you need to track behind and find the altitude and get to, it takes 2, sometimes 3 days to actually find the space station.
Well, I just use Heavens Above, or I use Stellarium with the satellites option. I plug it into the telescope mount. I say, go to ISS. And if the ISS is visible, it's going to go to the ISS. And if I get a wide enough field eyepiece, I can spot it once, and then it goes out of view because the satellites are moving really fast, and they're not moving like background stars or planets. They're moving really fast. So unless you've got the software in your telescope mount designed to accelerate the slew, it's like tracking a moving target. You've got to accelerate the slew because the slew takes time to get there. You've got to go past it, and then your tracking movement has got to be very much faster. You almost do nudge, 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 because there's no tracking speed that's fast enough. But there are some people on the internet that are really good at taking pictures of things like the ISS crossing the sun or crossing the moon.
He like go.
That's the one.
Yeah, he does really amazing pictures. Well, like you're talking about that picture that you have like a bunch of debris and it looks like all the satellites look covering the Earth. So whenever I see a picture like that, I remember Wall-E.
Yeah. The one that always bugs me, and it's still out there in the media, picks it up whenever they need to see. How much FUD can we churn? How many clickbaiters can we get with this picture? Is the Vera Rubin image from South America that shows you the large number of individual imaging chips that make up the telescope's imaging array, and they show you a field of like 8 Starlink satellites that had just been launched, zooming overhead of the observatory. See how bad they are? And you look at it and you go, first of all, you've overexposed the image because you can see from the background sky pattern what part of the sky they actually took a picture of. So you know the actual brightness. And you know they've overexposed it in order to make the satellites look bad. But then when you bring the exposure back down, you realize that the little black lines between the individual imaging chips account for a greater loss of background star presence in the overall image than the total collection of Starlink satellites that went through there. And then you look at some of the imaging chips, and big sections of the imaging chips are dead. One of the imaging chips, half the chip is dead, just black. And having looked at the Kepler Space Telescope when it was doing analysis for exoplanets, and realizing that whenever you have a galaxy or a really bright nearby star or a planet or a bright nebula, you not only take out that from the image, you take out a big chunk around it because there's so much cross glow that you lost all the dim stuff that's in that part of the sky. So when you start subtracting all this stuff out of the Vera Rubin image, you realize Starlink's no problem for them. They've got other bigger problems that they can do nothing about.
Yeah, the problem is like so many satellites around, it's the radio noise. Even though they have specific bands, it's still like a little bit.
No, it's not. The much greater radio noise is all the stuff here on Earth.
Yeah.
Your mobile phone community. When I was studying the Green Bank Observatory, they had a problem. What their problem was, there's a particular roadway that crosses their field of view if they get the dish down low enough. And what it turned out to be was that's a well-to-do community, and they have a bunch of people that bought cars that had self-navigation radars on them. And the radars, driving ahead, I want to see when I have to make sure the car panic stops to avoid running into the car in front of it, which means the radar has to be on all the time, whenever the car is driving. So if you've got a line of traffic facing towards the telescope's aperture when it's tilted down that level, all those radars are collectively going to be this horrific mass of radio frequency interference with all the reflections and the distortions in the field due to reflections of the terrain. The radars are behaving independently just fine. They're on frequency. They're not, too strong a broadcast. But when you line them all up from all those cars and you have it reflecting off of all of the buildings and mountainous terrain and everything else in the area, the secondary reflection frequencies that you're getting do affect the telescope. And they complained to the US FCC and said, you need to make all those radars 1/1000th their current power, or ban them, or register them all with the us so we know when every car is coming through. And the US FCC said, tell you what we'll do. We'll cut them all by 10%. Have a nice day. And they're not going to go out and say, we got to make sure all the radars in all the cars that you bought from every company on the planet suddenly have radars that are 1/1000th the power. And it ain't going to happen. Might as well just put up a giant metal fence around that, entrance to the radio telescope and let that be your Faraday shield.
Well, you'd think the guys who designed the radar know that they're only looking for a couple of feet around the car.
But radio waves don't know that.
Well, you can make it dim enough, so that it doesn't.
It's got to be strong enough so that you can discern, is it a shopping cart, which is its own Faraday shield, or is it a young child that could be just standing still, so you need a nice defined edge? So it's got to have a certain amount of power. And how fast is the car going? I mean, the car might be doing 60 miles an hour. What's your stopping distance? That's how far the radar has to go. But the part they really didn't think about was radio astronomy giant dish antennas facing in the direction of a line of traffic coming at them. Yeah. Well, correction is on you, radio astronomy. Okay. Anything else?
Crickets.
Crickets. Let me stop sharing.